this morning. But if you're ever wondering what's going on in this class, this is my Twitter feed. You're like, oh my gosh, how geeky is that? But you can actually get to it without going to the eCompanion site, and Autumn reminded me of this. You can get to it without even having a Twitter account. So up there at the top, I'll go ahead and kind of circle what that looks like. Basically, you need to go to the address is twitter.com, and then what follows that is my middle name's Ann, so Elizabeth Ann Snipes. So EA Snipes _ and then the name of this class. Okay, that actually will get you to this. And you might find this useful. I know most of you guys are here all the time, but you might find this useful if you're like, well, what's due when? So today, this is due. Is anybody, I know a couple people handed it in. Anybody else have this to hand in? Chapter 6 is due today. Now, the one thing, and I see a few people kind of working on their chapter assignments while I'm lecturing, everybody's different. I have found, I don't know how statistically correct it is, but a correlation, you know what I mean by correlation? I have found a connection between students working on their chapter assignments while I'm lecturing them, and also those same students kind of struggling on the exams. So it's good to be in lecture, but if you're working on something else while you're in lecture, that's almost like not being here. Okay, so everybody's a little bit different, but just kind of throw that out there. The other thing is we've got on here, and I don't know if I'll try to pull it up or not, how hard it would be to find it, but actually your next unit exam is scheduled for, and I think I said tentatively, for April 1st. So that's a Wednesday. There is a chance that, it's right here, okay? There is a chance that come April 1st, we're not quite ready for your test. We'll kind of see. But that's what I'm shooting for. And there's 4 chapters on this exam. Okay, so chapter 6 you just handed in, and then it goes in order. 7, 8, 6, 7, 8, 9. Okay, so there's 4 chapters. 6 and 7 are the longest chapters in this unit, and well, 9's kind of long, but 8's really short, air masses. Okay, so that's kind of where we're at. All right. So I was looking in my notes, and I could not find where we're supposed to start, and then I finally found it. And it was one of these where I thought we were actually going to start this on the Friday before break, but we didn't. So we're going to start here right now. This is where we left off. We just finished up chapter 6. We're ready for chapter 7. So there's an assortment of stuff in this chapter. It kind of starts out with something that's a little kind of straightforward, kind of what we call scales of wind. I'm hoping everybody remembers what creates wind in the first place, because we spent a fair bit of time talking about, I think there was even a quiz question. This would be high, this would be low. Basically, think of this as lots of dots, high pressure. Think of this as not so many dots. And it just, you know, if air is crammed someplace and it's loose somewhere else, it's going to go from that crammed place to that loose place. Okay, and that actually is wind. Wind is basically the movement of air from a high pressure to a low pressure. Okay? So here we see wind in motion. Okay, we see wind can be our friend, and it blows our ships, our sailboats, or wind can be kind of more damaging than that. We can actually see wind in motion here, can't we, with the, kind of the clouds. This is like a satellite image of the cloud motion. This is be an island, so basically you have a prevailing wind here. You have an island providing some friction, and then you have it kind of swirling around it. These are like eddies, right? Yeah. So this first part is kind of straightforward. I like this chapter. It's got, like I said, kind of a mixed bag in it. So there's 3 scales of wind. It's kind of like the papa bear, the mama bear, and the baby bear, okay? So there's the big scale of wind, we call it macroscale. There's the middle size wind, we call that mesoscale, and then there's the small wind we call microscale. So macro, meso, and micro. Macro big, meso middle, and micro small. So these have a size thing to them, like I kind of mentioned, but they also have how long they last sort of thing to them. So basically the biggest ones last the longest, and the smallest ones last the shortest amount of time. And you can already kind of see some examples of those. So for instance, if you've ever seen a dust devil, Okay? Dust devil, it's small and it doesn't last very long. Microscale. We're going to talk about, let's see, not in this unit, but the next unit we're going to talk about hurricanes. Hurricane is actually our specific name for a tropical cyclone. So those are actually macroscale. And then in between, I don't know if you remember, but in chapter 6, we talked about a sea breeze. That's kind of an in-between sort of. Well, actually, we're going to talk about sea breeze again. We talked about chapter 6 and chapter 7. Remember I said if you're ever like give a kind of a wind like that, you have the word breeze after, you're like, well, where's it coming from? Well, it's coming from the sea. Okay? So those are kind of scales of wind. And kind of from left to right, you have the macro, the meso, and the microscale. Macroscale, mesoscale, microscale. I just think it's almost I like seeing like dust devils and stuff like that. I like seeing little things fly around, and sometimes they don't go in straight. They kind of have like those eddies, like those little kind of little circles. Kind of creeps me out, but I like it. Here's a figure from your textbook. I like it. Now it's going from small to large. So, and underneath it, okay, so this is your microscale. This is the smallest. Okay, and it's reminding you that this actually, in the green is how big it is, okay, and here is how long it lasts, okay, so it's small in size, small in duration. Okay, then we go to mesoscales, and notice that some things like tornadoes and thunderstorms, they kind of overlap between micro and mesoscale, okay. That actually then has a moderate duration. Then we go here to the large scale, macroscale, okay, and they can last, you know, up to weeks and be very large. So we're going to focus on mama bear, the middle ones, okay, the mesoscales, okay, which are moderate in size, moderate in duration. These are all what we call mesoscale winds or local winds, and local winds just means it's local, okay, it's because of some sort of kind of local phenomenon that's creating them. So these actually, somehow I'm going to test you over them, so kind of pay attention. We're going to take one at a time, okay? But they are all created, as we talk about them, you know, look for the high and look for the low and look for the wind as we talk about each of them. So this one's do-over. So like I said, we actually talked about sea breezes in the previous chapter, and I have another figure to show you. But a sea breeze happens because the land, I kind of find the word land, because the land heats more quickly as the sun rises. The land heats more quickly. So if the land gets nice and toasty, it gets nice and warm, and basically I said warm air creates a low pressure. So basically your ocean's lagging behind or your sea's lagging behind. It's cold. You have a high pressure there, a low pressure here, and voila, okay, it's what we call an incoming breeze, okay. Sea breeze, this actually is the same phenomenon we run into in Chicago, the lake effect wind. Mm-hmm. Yep. But as the sun sets, basically, we kind of have the opposite thing where the sun's not out anymore and the land is going to cool down more quickly, so it'll get nice and chilly. That warm water is going to retain its heat. So basically, we have a high pressure here, a low pressure there, so we have an outgoing breeze. Okay? So these are those two. Okay? Like, well, how do I know what this is? Well, look down here. Notice you see the movement of air, okay, from the sea, okay, or Lake Michigan to the land. That's the sea breeze, okay. And we have an outgoing breeze at night. All right. So we have another pair of breezes that actually go day-night again. And these will work best if you have basically kind of a valley situation, which you have a mountain on both sides. Okay, so mountain, a valley in between. So here's the deal. You guys have been telling me as you climb a mountain, the air gets thinner. Thin air is more susceptible to, it will heat quickly and cool quickly. Thin air. Okay, so here's the deal. Okay, that thin air up there, when the sun shines on it, okay, it goes ahead and heats quickly, and warm air has a, warm air has a lower pressure. Okay, so basically, okay, you have, this is called the valley, right? This is my V, mountain valley. Okay, so basically you have warm air up here, that's your low, and so it goes, okay, it's your valley breeze. Okay, then you're going to see here in a minute, when the moon comes out, okay, the sun goes away, basically that thin air is going to cool quicker. Okay, so if it's cool, it's basically going to have a high pressure compared to your valley. Okay, so then you have a mountain breeze. So those are the two. So you have a valley breeze in the daytime, a valley breeze in the daytime when the sun's out. Okay, now if you have a cloudy day, not so much, right? Okay, because you're counting on the sun basically, affecting the thinner air more than the thicker air. And at night you can have a mountain breeze, which would be a downslope breeze. So here they are. And this goes ahead, and I'll show you the other picture. So this goes ahead and says if you have that kind of what we call a valley breeze, okay, that actually can be a lifting sort of mechanism. That chunk of air that's there along for the ride, actually it will expand and it will cool, and it can cool to the condensation temperature, and you can go ahead and get actually clouds forming over here. Wonder if they're lenticular clouds. I don't know. Okay. So this is the third local wind. Local wind, mesoscale wind, they're the same thing. So this one, we have two winds coming up that deal with mountains. Okay. This isn't necessarily a valley, but just a mountain. This is called the Chinook wind if it's associated with our Rockies. But if it's in another continent, if it's associated with the Alps, would that be Switzerland? Okay, good. I think so.
Yeah.
The Alps are in Switzerland? Okay.
A bit geography.
I've never skied them, but the Alps, okay. This same wind is called the foehn wind, okay. Notice it's on the leeward side, which, so if this is west, this is the Rockies, and the wind comes from the west, this would be the leeward side, okay, Rockies, windward side, leeward side. Okay, so it's on this downwind side. Now here's the deal. If you were to look up Chinook, the definition of Chinook, in Indian language, it means snow eater. So here's the deal. You know, you think living in Iowa, we have these temperature swings, okay? But if you have this downslope wind, okay, it's called a Chinook wind, if it's associated with the Rockies, basically it can go very fast, 90 miles per hour. But the other thing is, one of the things to talk about air that is going to go down like that is as it gets smaller, it compresses and it gets warmer. Yeah. So basically you can have a 40-degree Fahrenheit change, which it seems like we've had some of those swings this past few weeks. Yeah. We haven't had Chinook winds, but we've had some crazy temperature swings. Okay, so that's the Chinook wind. And I think I might, no, I guess I don't have a video for one. So another downslope wind, you've heard, and I'm going to play this little video for you, but you've heard of the Santa Ana winds. If you're like me, I can never remember how to spell Ana. It's with one N. Santa Ana winds, okay. Now, it's a downslope wind, but it's on the windward side of the Rockies. Okay, and both the Chinook wind and the Santa Ana wind, in order for there to be a wind, basically you have a high pressure on the top and a low pressure down here. And okay, so let's play that video after I plug in what it should be with regard to precipitation. The water tables are low. What's that? Get some cloud seeding going on? I don't know. But the other thing, oh yeah, I know, the thing I heard on the radio said they have 1 year left. I'm like, dude, I don't know about cloud seeding, but maybe so. I mean, they have 1 year left using water at their current rate. And my husband was saying, you know what they need to do is go brown. I mean, why do they need to have a green lawn when they're like in the desert, you know?
Yeah.
That would help a little bit, you know? So they're trying to fight Mother Nature, I think.
Just put some turf down.
Yeah. You know, go with it,
You
right?
don't have to do anything with that.
Exactly. Turf. Plastic, right?
Yeah, I think
Yeah.
it's some type of plastic.
You know?
It looks pretty real though. I mean, it's really green, but
Yeah.
that's what you're going for, I guess.
So the 3 winds we've done are the sea and land breeze, right? There's more to come. The valley and the mountain breeze. We talked about the Chinook and the Santa Ana. Those are all local winds, mesoscale winds. The katabatic winds need a plateau. So let's see if I can make a little plateau down there. So go back to your days in, I don't know, whatever class you learned this, but a plateau is basically kind of a landmass that has steep sides, okay? And so actually, Greenland fits that bill. So it has water on either side, and it has steep sides, okay? So no pun intended, the good, or the way to get katabatic winds is also it needs to be in cool temperatures, okay? So basically in Greenland, it gets this cold air, okay, kind of the cold air on top of the plateau kind of builds up. And so one of the things we know about cold air is nice and compact. So cold air actually is a high. So I'm going to choose a different color here. So actually that air up on top of the plateau, okay, that cold air kind of creates a high. It builds up, and kind of like if you had kind of a ledge like that, or something that had a ledge, and you piled stuff, and if it was some sort of fluid like liquid or air, at some point you're going to have too much there and it's going to slough off. And actually it's that sloughing off that is your katabatic wind. So I'll just kind of over here on the left side kind of show it. Basically that high builds up and it basically sloughs off. Okay, and that's your katabatic wind. So it'll go down the slope and in towards the sea, okay, but it's wind. And it can, like the slides say, it will recycle, repeat itself. Okay, so that was katabatic winds. It needs a plateau like Greenland, works real well for that. In case you're asked on a test, hint, hint. Feel free to draw pictures on your test, remember. Country breezes, remember I said the word before breeze says where it's coming from. So country breeze comes from the city. Country breeze comes from the country in towards the city. So if you read this description, it kind of looks like this. If these are my skyscrapers, okay, these are terrible skyscrapers, okay, but they're concrete skyscrapers, and basically it can get nice and toasty, hot, okay, and sometimes you might see the word hot and you think hot H, hot. No, hot air is nice and fluffy, so actually that's a low pressure, okay, that's in your city. It's kind of a low pressure because of the concrete. And the other thing is it's hot because it's called the urban island heat effect. I think your textbook addresses it, but I pulled it from my notes. Urban as in city, island as in it's surrounded by country, heat effect. Okay, so basically you have that low pressure, and then I'm going to kind of draw outside here in the country. You have a high, okay, so this is all country around it. So that's basically why they call it a country breeze. Okay, so it's like wind moving from the country into the city. So we would call that convergence. Air is converging there, isn't it? Yep. And so one of the things is if your city does have a pollution issue, that sort of thing, one of the things that converging air will do is it's like, whatever pollution you have, you're probably going to keep. So this actually can aggravate pollution. Okay, so that's country breeze. All right. What do we got next? Probably running out of breezes. Right. So that was our last middle scale wind. That was our last local wind. And those were all local winds. Now I put this slide up here to kind of put things in perspective because we're going to switch gears and we're going to go to macroscale winds. Okay? So macroscale winds. Back in 1735, and I wish I knew more about history, but I imagine they were sailing and doing all that sort of thing by then. When did Columbus sail the ocean blue?
1492.
Thank you. Was it 1492?
Because the rhyme. Okay. 1492, Columbus sailed the ocean blue.
So Columbus actually was sailing before we understand what I'm going to show you about easterly trade winds. Have you heard Columbus took the easterly trade winds? Well, he did. Okay. Large scale winds, easterly trades, large scale winds. So before we knew about the easterly trades and that sort of thing, this guy came up with this cool idea. It's just what we call a single cell. One of my pet peeves about this subject is you're going to see it wasn't just one cell. It was a cell in the northern hemisphere and a cell in the southern hemisphere. So, I mean, we're talking big winds. So basically what he said, and he was right, okay, he said that one of the things you knew before you came in here is if you were going to go towards the equator, it'd go hotter, right? Okay. He said with all that warm air, now don't think high pressure or anything, but think of that warm air wanting to be buoyant. Think of it, warm air rises, okay? So what Hadley said is that warm air is going to rise, okay, and it's going to hit the tropopause, because this is the troposphere. It's got a lid called the tropopause. Then we go to the stratosphere, the mesosphere, the thermosphere, okay? So in the troposphere, topped by the tropopause, he's like, okay, so that wind rises here, it hits the tropopause, and this is why I say it has two cells, because that's my two cells. He says it was one cell here and another cell there, okay? And then he said what happens is it will go to the poles, it will sink, and then it will ride the surface of the earth. Come here and rise. So you kind of have like this. It rises, hits the tropopause, goes here, sinks, okay? And really, to understand what I'm going to try to show you, you kind of have to think 3 dimensions. See how I've lifted it off of the globe, okay? Okay, so that's Hadley's single cell, really 2 cells, okay? And it's a good place to start. So instead of the single cell, which is really 2 cells model, actually nowadays we have what's called the 3-cell model, which is really 6 cells. Okay, so we have 3 cells in the northern hemisphere and 3 cells in the southern hemisphere. So I'm going to play this little video for you, then we'll kind of talk about it and dissect it. But if you're, you're going to want to or need to be able to kind of wrap your mind around it one way or the other. Let me show you the cells. Here's the first cell, here's the second cell, and here's the third cell. In the southern hemisphere, 1, 2, 3. And again, it's kind of, this figure is pretty good. It's trying to show you kind of the 3 dimensions of it. Okay, so we'll be talking about those, but let's see what the video does. Okay, so she talked about the Hadley cell. Now, a little bit ago on that figure, I kind of showed you 3 cells in the top and 3 cells in the southern hemisphere. This cell right here is called actually the Hadley cell. There's a thing coming up here in a minute. But Hadley, who had the 1 cell in each hemisphere, he was right. Basically what they have, one of the things they have in common was what the video emphasized, I think, was the warm air rises, hits the tropopause, and goes both directions, but it doesn't go all the way to the poles. It only goes to about 30 degrees latitude, and then it descends. Okay, that right there are your pair of Hadley cells in the northern and the southern hemisphere. Okay, so Hadley cell is only one of 3 cells in each hemisphere. So there's a northern Hadley cell and a southern Hadley cell. Okay. And it does start about the equator. Okay. Yet today, I'm going to have to actually change that a little bit. What we think is always hot, right, zero latitude, that's the equator. We think that's always hot, but not necessarily. What's really, really hot is something we call the ITCZ. And those 4 letters stands for intertropical, convergence, zone. Okay, and that is, I'll put equals hotspot. That's the real hotspot. Okay. So just to kind of make sure, full disclosure. So this says that it descends, this says about, instead of 30, it says 20 to 35 degrees latitude in each hemisphere. Okay, so that's your Hadley cell. So let's think about that descending air, especially when we talked about, when Dirk explained the descending air with the Santa Ana winds. Yeah. Basically that air about here that's going to come down, it's going to squish together, okay, and it's going to warm. If you look about 30 degrees latitude, oftentimes on your continents, that's where you're going to find your deserts. Okay, so here, yeah, this line right here is 30 degrees. So actually it's going kind of in the south part of Texas right there. Okay, that's 30 degrees latitude. We're about 42. Okay, 30 degrees. So that descending air oftentimes is dry and hot. Okay. So we have a three-dimensional sort of thing going on with these macroscale winds. The winds about 30 degrees latitude, the word variable means that you can't count on them, right? Okay, they're light and variable, the winds are, and they are nicknamed horse latitudes. So I don't know, anybody in here like horse lovers? Okay, so close your ears, Ashley. But like in the old times when they wanted to use the winds to get like from between continents, if the winds petered out, they'd start making their ships lighter, and they would throw their horses overboard. That's why they're called the horse latitudes. I'm sorry. So, but they were desperate, right?
Oh yeah.
Yeah. So here's the deal. Again, you have to kind of think in three dimensions. The thing about that air, okay, coming down about 30 degrees is it splats, it hits the earth, and it goes both directions. Okay, so part of it kind of, what we say, completes the Hadley cell, and part of it goes north. Okay, yeah. So kind of hold that thought, and actually, can't believe my slides have been wrong for, well, this hasn't been 12 years worth of slides, but probably 3 years. So in your slides where it says southerly, you need to put northerly wind. The word northerly wind actually is describing the direction from which the wind is flowing. So this is talking about that wind, that air about 30 that splatted, it hit the Earth's surface, and some went this way and some went this way. The one that's completing the Hadley cell actually is a northerly wind. All right, so if you're with me here, now you got to think about the Coriolis force. It deflects to the right. So I'm on top of the globe. I'm a northerly wind. I'm deflecting to the right. Okay, that actually at the Earth's surface is why we have our easterly trade winds. That is an easterly trade wind. Okay, that creates our easterly trade winds. And they're actually not due easterly. They start out as kind of their northeasterly trade winds. So you have another fix here. In the next little bullet where it talks about the southern hemisphere, Hadley cell, basically that wind splatted, and it needs to go to the north. It's a southerly wind for the southern Hadley cell, and it's deflected to the left, and to the left it creates another easterly wind. So here, if I kind of make this my surface, okay, if this is my surface, not my upper wind, basically I have, make sure I get this right here, I have a wind going here. That's your NE trade winds, northeasterly trades, okay? And we have a wind coming like this, okay? Your southeasterly trades. Okay, those are winds at the surface. That's what, I almost said Noah. That's what Columbus used, okay? And check this out. I love it when like science things kind of come together. Do they look like they're converging? Okay, that hot spot there where the Hadley cells bump up to each other, that is actually what the sea is in intertropical convergence zone. Isn't that wonderful? Yeah. So where they converge, it might look like there should be all sorts of wind available, but That's not necessarily the case. There at the ITCZ, at the Intertropical Convergence Zone, it's a prevailing easterly, but it's not always so intense. The word doldrums, if you're in the doldrums, you're kind of like, blah, okay. That actually is what they call those. So we have the horse latitudes about 30, the doldrum at the Intertropical Convergence Zone. Yeah. All right. So on either side of the Hadley cell, we have a pair of ferrule cells. Sometimes I spell this wrong. What's that? Yeah, ferrule like wild, exactly. So ferrule cell, ferrule cell. Okay. Then it goes about from 30 to 60 and from 30 to 60. So I said we're about 42, so that's us, right? If we're about 42 degrees north latitude, we're about here. So we are under the influence of, we are in the ferrule cell. You feel wild? Okay. So here's the deal. Let's finish that thought with the descending air of the Hadley cell, or kind of between the Hadley and the ferrule cell. And instead of going south towards the equator or the intertropical convergence zone, let's go north. So as we go north in the northern hemisphere, it's deflected to the right. So actually we have a surface wind that is a westerly surface wind. Okay, so here we go. These are what we call the mid-latitude westerlies. I'll just put, yeah, I'll go ahead and say mid-latitude westerlies. And guess what? Down here, that descending, or the air going towards the poles, actually, it's deflected to the left. So they actually also have a westerly down here. Now they're mid-latitude westerlies. Now here, before we leave, I'll show you that it's not quite this simple because we have the whole water landmass thing going on. So, but that's kind of what's going on. Okay. So and it's not always this simple, but if you go 30, 60, 90, you kind of split the hemispheres into 3 sections, gives you your Hadley ferrule, and the top one we're going to call the polar cell. Yep. So there about 60 degrees or so needs to be the end of the ferrule cell. So basically air is going to rise there again. So it falls kind of at 30 and it rises at the equator or the intertropical convergence zone and between the ferrule and the polar cell. Okay. So in order to talk about that last cell, what I like to do is just kind of think of, if you're at the top, you know, if you're at 90 degrees latitude, okay, so it's 60 to 90, basically think of that cold air as descending, kind of like, I think of it as like taking an egg and cracking it and letting the egg kind of drip all over the surface, okay? So basically think of it that way. So that air that is going from the poles towards the equator, it's deflected to the right in the northern hemisphere. So did that make me another? Oh, let's do this. Okay, good. See, I had to convince myself. You guys see how if I'm going down, I'm going to be deflected to the right, and what direction is that going? It is going east. So actually, nope, it's going east. I'm going down, deflection to the right at the surface. No, it's going west. Thank you. It's going west, but we name it for the direction it's coming from. We're both, okay. Yeah. So it's going west, and we call it easterly. Right. Okay. Good. Easterly.
The names of them is where they come from, not where they go to.
Okay, so here we have what we call the polar easterlies. And not so surprising, we have an extra cell down here.
Oh,
That's weird. Okay, yeah. 90, that's like, okay. Here we go. Here's the polar easterlies. direction from which it's blowing. Okay, those are all surface winds. And that top one, I'll go ahead and put the word here in a minute, but those are polar cells, a pair of polar cells. So here you have, instead of one cell, which is really two cells, right? But in each hemisphere, instead of one cell, you have three cells. And so, Hadley, a lot of times in science, Hadley got the ball started. That's the way I think of it. So these are a pair of polar cells. Very cool. Okay, so, like I said, you got to think 3 dimensions. And in weather, if you're not thinking 3 dimensions, you're probably, something's not going to quite be right. So you got to think of what's happening at the surface, and you got to think what's happening here at upper elevations in a way. But at the surface, we kind of have this going on, okay? This is all surface stuff. This is your hot spot, your intertropical convergence zone. It may or may not be at the equator. Okay, you have a pair of easterly trade winds. Okay, this would be what, the Hadley cell, right? Okay, then we have that air that's descending between the ferrule and the polar cell. That descending air creates what we call just kind of a semi-permanent high. Okay, and then we have the polar easterlies near the poles, obviously. So kind of breaking this up, these are Hadley cells. Hadley cells, you probably recognize those. These are ferrule cells with 2 R's and 2 L's. Okay. Nope. Ferrule cells are here. Okay. And this is the polar cell. All right. So that's idealized, but I mentioned this before that that's not the way our Earth is. Our Earth definitely has, a minority. It's like 70% of it or something. Maybe 20, sorry. It's like 3/4, 2/3 water. Okay. So only a fourth or a third of it is land mass. So the thing about land masses is it throws a kink in the whole thing that it heats up and cools down differently. Okay, so. Yeah, and it also causes friction, yep. Yep. So one last thing I want to get to is kind of how our hot spot moves. I'm glad to finally get to this slide. I talked about it earlier today. So it's the hot spot. It's not necessarily the equator, but it's called the intertropical convergence zone. What's converging there? Actually are trade winds from both hemispheres. Okay? So not so surprising, as the Earth orbits the sun, and the direct rays of the sun kind of vary where it hits with regard to latitude, that thing's going to move too. So that we actually have we have a semi-permanent high pressure that's actually, remember that descending air that creates our deserts? That creates a high pressure right there, okay, between the Hadley and the ferrule cells. Okay, and we have actually 2 lows, 2 semi-permanent lows. We have a low where the air is ascending at the intertropical convergence zone, and we also have a low there between the ferrule and the polar cells. So what I'm wanting you to remember is, in this unit we talked about anticyclones and cyclones. And actually a high is called an anticyclone.